Stan Meyer said the VIC was the heart and soul of his invention. But what is a VIC? It's a voltage intensifier circuit. Meyer claimed that it could split water into fuel with a fraction of normal energy. Genius? Fraud? Today we start the journey to find out. Part 1 begins here with the humble optocoupler on a breadboard. The VIC is Meyer's mysterious black box. Before coils, tubes, and high voltage, we need control. Safe, isolated switching between the Arduino brain and the power stage. That's where the 4N35 comes in. I'm going to put the Nano test code in the comments. If I forget, please remind me.
Is there anything you wish you'd known before you started?
At first there was nothing, no blink. Why? Because the Nano pins weren't seated, and I hadn't soldered the headers. A press fit isn't a connection, it's a hope. Once I pressed down on the Nano, boom, the heartbeat came to life. Lesson learned, solder early. This is the initial test of our pulse control system, built using the Nano, the optocoupler, and a logic level MOSFET. The Nano is running a simple test sketch. It's toggling digital pin D3 on and off every 500 milliseconds. This square wave acts as our control signal. We're routing that pulse through a 220 ohm resistor into pin 1 of the optocoupler. That's the anode. Pin 2 is the cathode, and it connects directly to ground. On the output side, we connect pin 4, the emitter, to ground, and pin 5, the collector, gets pulled up to the 5 volts through a 10K ohm resistor. This creates a clean digital high when the transistor is off and pulls low when the pulse is active. That pulled up signal at pin 4 goes straight to the gate of the MOSFET, acting as our switch controller.
Anything else?
My soldering iron. My finger kept changing the temperature without me noticing. One moment nothing melted, the next I was burning pins. If you're building alone, double check your gear. I just bought the new soldering iron, and that's why that was happening. For now, we're using a simple LED and a resistor as a load between the drain and the 5 volts. The source is tied to ground. When the gate pulse is high, the MOSFET conducts and the LED flashes. And that LED right there, it's our proof of life. It blinks because the signal is flowing, but it wasn't always working.
And the last one?
I also forgot jumpers from the Nano 5 volt to the ground rails. Well, from the Nano to the 5 volt and the ground, and the Nano ground to the ground rails. It was a rookie move. Without it, nothing works. Once added, everything lit up. Simple mistake, but worth sharing because it cost me some time. This confirms the pulse path is functioning and the MOSFET is triggering as expected. We verified opto-isolated logic control. With this stage complete, we're ready to add inductive loads, resonance tuning, and voltage intensification. This pulse is verified. Something I wish I'd realized sooner, something else. With 220 ohms, the Nano pushes about 17 milliamps. It works, but it stresses the pin a little bit. A 1K resistor is plenty and safer. Same with the 10K pull-up. It's functional but slow. In part 2, we'll fix these values for snappier switching. A few other edits may be beneficial, but I'm getting off track for this video, and we'll also include those in part 2. So far, we've got the Nano, 4N35 octocoupler, an IRLZ44N MOSFET, some resistors. Right now we're just using 220 ohms, 10K ohms, and 330 ohms. We have jumpers, LED, breadboard, USB cable for uploading the code. Simple parts with big potential. This stage proves our pulse path works. The Nano, the optocoupler, and the MOSFET are all talking. The heartbeat of the VIC is alive. In the next phase, we'll add coils, resonance, and voltage intensification. That's where the current steps back and the voltage climbs. And that's where it gets really interesting. If you want to know whether this legendary circuit works or collapses, subscribe and follow along. This isn't theory, it's hands-on. We're chasing Meyer's ghost, step by step. Okay, so if you are building along with me, here is a quick reference to what we have wired. The Nano D3 to a 220 ohm resistor to the 4N35 pin 1. 4N35 pin 2 goes to ground. 4N35 pin 4, which is the emitter, also goes to ground. 4N35 pin 5, which is the collector, goes through a 10K ohm resistor and to the 5 volt rail. The 4N35 pin 5 collector also goes to a 220 ohm resistor into the MOSFET gate. The MOSFET source goes to ground, the MOSFET drain goes to the LED cathode. The LED anode goes to a 330 ohm resistor and to the 5 volt rail. The Nano 5 volts goes to the 5 volt rail, and the Nano ground goes to the ground rail. That's it so far.